Good afternoon. Hello. Welcome to the Sunday Science Q&A. There's no more sun anymore. I mean, it may well return, but as David Hume said, we can't be certain it'll even be up again tomorrow, but that's the way philosophy works. But it is pouring with rain, so hopefully this is the kind of thing that will bring you happiness, understanding the structure of the universe, why matter is matter. All of these things are, they'll bring you jolliness, just seeing the possibility of human endeavours. I was just thinking, I don't know what Helen thinks about this, just before we came on air, we've had a bit of a struggle technically, which was all my fault, which is a little bit talking about the presidency, which is because quite a few Trump followers believe that COVID-19 is a hoax. What will they think about the fact that their president is now part of that hoax? There's a kind of intriguing thing about that.
That was my first thought as well, and I actually did go and look. I did go and dig around the internet to see if anyone had answered that question. And the what I found, which I guess is exactly what people like Dallas Campbell, who are all into motivated reasoning, would predict, is that there are even more convoluted conspiracy theories about him tricking the deep state into thinking he's ill or something like that. So I don't know, but there's definitely some really interesting mental contortions going on to deal with that, I think.
And that's why I prefer the simplicity of both particle and theoretical physics. Doesn't it all seem so easy after you observe human behaviour? I should quickly tell you, we did do another of our genetic shambles that went out. It's in fact, we've also cut it up into different pieces. We had a lovely time talking about just different ideas about COVID-19. It's you can hear it, or you can also watch a version of it where we did talk about different things, such as what we're learning about the implications of long COVID, why the current scientific belief is now definitely that masks are useful in terms of hindering the spread of COVID-19, why it's highly unlikely it was manufactured in a laboratory, and various other things about COVID-19. So that's up. I'll just tell you a couple of other things. Also, we've got a load of science shambles coming up, which is me talking to different, predominantly at the moment, people who have books out, but generally we're going to be talking to scientists. We may well change the name of that to Chaos of Delight. We don't know, but coming up soon is a fantastic book, which we talked about the other week, and I know that Helen has also talked to Joe Marchant about this, Human Cosmos. Really good. Stuart Clark has also written. We'll talk to him about some things. And this book, we're going to have a conversation very soon with Rebecca Ragg Sykes, who was also on a genetic shambles not that long ago, talking about Neanderthals. But Kindred is an incredibly beautiful book written about what we now know about Neanderthals. And I also found out during the interview that this is a beautiful thing to know about the popular press, that Neanderthals are now considered to be clickbait. Now, that to me is an advance. That is, one of the reasons the COVID-19 Neanderthal story went up, even though, there is a certain amount of debate, of course, of how much actually, knowledge there is in that accurate. If you put Neanderthals into a headline, clickbait. That's a good thing, isn't it, Helen?
Well, I think it's progress. I'd rather that. I hate clickbait. I am the sort of person that hates book titles that are really obvious questions that follow that law, where if the answer is no, you shouldn't, it's not Bethany's law. Which one is it? All the laws.
Yeah, I know. Yeah.
But I guess it's sort of progress, because you can definitely sneak in proper science. If it's somebody's, I don't know, some conspiracy theory about a hamster eating all the crucial papers, then it's harder to sneak science into that. But at least if it's Neanderthals in the title, we scientists can get in there and maybe get some proper science in. Not that we're desperate.
Any Trojan horse that you can make by,
there is
you make it and sneak it in.
Really good solid mechanics in the construction of a Trojan horse, I'll have you know. There is really nice engineering that has to go into how you do that.
Well, we should mention actually another interview which is just up online at the moment, because we're talking about the classics, Pandora's Jar, which is all about Natalie Haynes' new book about women in the classics, and how over periods of time those women in the classical world, how the stories have been changed to fit in with, I suppose one could probably say quite often, a patriarchal society. It's a fantastic book. I really enjoyed reading that this week. I'm going to introduce you to our guest in a moment. As I said, this week we are doing particle, theoretical, and all manner of other forms of physics, and probably there'll be some questions on bubbles, and it will be the physics of bubbles, because Helen always normally gets a few of those. Mention our Patreon account as well. We're making lots of shows every week. I think on average we make about 4 shows a week, and quite often we make more shows than that. And I'm pleased to say that we get thousands and thousands of people who both listen and watch, but only about 1% of them actually donate or do anything. And that's fine in one way. That's fine for all of those of you who this is a very worrying time for many people. But if any of you do have a little bit of spare cash and you want to kind of support us, especially because we're not doing any live work, all of the live things in terms of in theatres not there. If you can support us via Patreon, we would love to get 5% of our listeners and viewers supporting us via Patreon. 95% of you still free, but are you in that 95%, or can you be in that 5%? Check Cosmic Shambles to find out about our Patreon details, and also just give a heads up for next week. Next week it's archaeology, and so if you've got any questions about archaeology and generally the digging sciences, then we can deal with those as well. Today's guests are, as I mentioned, now someone who I've done a few things with before, lecturer in particle physics at Queen Mary University, and also you can hear her on, we did a documentary about Richard Feynman, because Radio 4 didn't want to do a documentary on the 100th anniversary of the birth of Richard Feynman. We took it upon ourselves to do it, and there is some music in there as well. We have some songs that were composed especially for it. We don't have as many bongos or tap dancers as I would have had if we had some kind of budget, but a lovely conversation that I had with Dr. Linda Cremonesi, who's great to have you back with us. How are you?
Hi, Robin. Hi, Helen. Yeah, great. It's really lovely to be back here, and being able to keep doing this even in this difficult time.
Well, I should actually, that's the thing. One of the things that we have got a special announcement on Wednesday about one of our, probably the most ridiculous kind of science show, which we are doing because the theatres are not around. We've got a little bit of a plan as well ahead, and I hope you're going to be part of that as well. And we also have Achintya Rao, who is was based PhD student, lead science educator at CERN, which is an incredible place to have to communicate science as well, because those ideas, so many people don't even know. It doesn't cross their mind, I suppose it would be fair to say, and in the first place, that there is something needed to mean that matter is matter. Would that be fair to say?
I'm not entirely sure how I want to answer that question, Robin. Let's just skip that for now. But yeah, it's nice to be on with you, and I am complimenting you as the second professional idiot on the show, because I, unlike the others, do not have a PhD in particle physics or science in any way. I am a student of science communication, and I work doing the sort of particle idiot's job of translating the research into something that can be understood by others. So
you see, at least you're able to translate, though. At least you're a fish of science, so that already is something more impressive than I. You can be the babel fish, I will be the professional idiot. Now let's find out what show and tells people have got. Helen, have you got show and tell for us today?
I do.
You must be running short of these now.
They're getting more practical. I think that's what's going about. So I've got this bit of setup. So what I've got, this is genuinely what I've spent this morning doing, right? So
wow, that's danger.
So this,
close to the microphone.
You can try at home, right? Shall I go on this side, because then you can maybe hear me a bit better, right? So I there's random questions that go into your head, and I was thinking about apple bobbing. And I thought, why does no one ever do pear bobbing? This is genuinely the sort of thing that goes in. So this is water. I've got an apple here. There we go. The apple floats. That's very good. I've also got pear, which sank like a stone. And there's a reason for this. So it turns out, you've probably seen these things, that the problem is, once you start this game, it goes on for quite a long time. So the kiwi fruit sank. Lemon floats. This was, no end of fun here. So what is going on is that, first of all, you can try this out with any fruit and vegetables you've got. But what it is that basically it turns out that fruit needs to breathe. And apples are 24% airspace, because they've got big cells and big air channels, and that means air can go through and help the apple breathe as it's growing, and actually after you've picked it. Whereas pears have really small cells, and their air channels are really thin and narrow, so they're only 5% air. So that is why you can't go pear bobbing. But you can play it. So it occurred to me after a bit, I've got too many things in here now, that now I've got wet fruit everywhere. So your question, right, there was this, we know why this is relevant. Regular viewers of the Infinite Monkey Cage will know exactly why we have to put a strawberry in here, and I have not done this. I genuinely don't know what's about to happen. Strawberry floats. So strawberries need lots of oxygen. That's what that's just telling us. So obviously what living cells need is to respire. So they take in oxygen, they burn fuel effectively, they give out carbon dioxide. And the fruit that floats has a better structure of channels and air spaces for breathing. So what are these? Blueberries float. So I think most of these things are going to float.
Blueberries have sunk. Blueberries started off positively, but they've given up.
You know what? One blueberry
anxiety of being a blueberry.
One blueberry went down and one blueberry went up. See, that one went down and stayed down, and that one's gone up. So
now that must mean that some of those blueberries are off. That's what I'm reckoning. It must be something about how much blueberries fermented or. What we're going to do the next time we do a live show, Helen, you're on stage for the whole of the show, especially if we ever manage to do a Christmas one again. And I want you to have a huge bowl and you can make punch while also at the same time telling us about the properties of fruit. I think that's a...
The lime sank and the lemon floated. So anyway... Should you be bored this afternoon when it's raining, I highly recommend getting every fruit and vegetable that is in your cupboard or your fruit basket or your whatever and doing this. Because the thing is, it is telling you something quite exciting about the insides of the fruit. And the reason we know this, by the way, is that and apart from this, the first time anyone could find out about this was people got X-ray tomography machines. People have genuinely put apples in synchrotrons to do imaging of the inside of the fruit, to look at all these tiny channels and pores, and to find out that apples are 24% air. So anyway...
Well, I think the nice thing is tomorrow we will see in Campaign, the magazine of the advertising industry, just won the part of the next year's summer campaign for PIMS. So well done. That was a beautiful audition piece. Linda, what is your show and tell?
Right, so I don't have a show, but I have a tell that actually goes pretty well with what Helen just showed. So Helen, can you keep your jar right there?
Yeah.
I mean, like you can show your face as well, so that.
Oh no, that's really good, because now the way that actually the base of the fruit lined up, it actually looked like that great Dutch painter who used to those paintings of faces using fruit. So that's a fantastic image. You currently have an apple and lemon eye.
Good.
Yeah.
Right.
So
Who
Helen
said there was any divide between the two cultures of art and science?
There's no divide, because science is an art. So Helen talked about tomographies, and actually the link that I have here is that you can use particle physics to do tomography. So we can use the particles that we get from, so there's this particle called cosmic rays, and cosmic rays come uniformly from pretty much all around us, and they're charged particles. They're actually protons, and when they interact in the upper atmospheres, they make muons. The muons are these, they're like a lepton, but just a little bit heavier and more stable. So a muon will be able to travel like for a really long time. So you can use this flux of like uniform muons to actually use tomographies. So in a similar technique to what Helen just explained, if we can imagine like to have on one side of the jar some scintillator plates which are able to actually see these muons, and then some other side on the other side, then you could make an image of the inside. But what's really interesting is that this technique was used in the pyramids in Egypt to actually find out if there were any hidden chambers. And for a long time it was used, and none were found until I think it was a couple of years ago, that they did find in a hidden chamber. And all they did was to put some of these scintillator plates. And when I say scintillator plates, I mean they're bits of plastic. So you can imagine this like highly transparent plastic. And within the plastic, you can put some fibers. So when the muons go through the plastic, they emit a little bit of light, scintillation light, which then gets collected. So by measuring the muons that were on one side of the pyramids and the muons that got to the other side of a wall or a space, then they could actually have an image of the inside.
That's beautiful. Thank you. Can I also ask, because we were talking about, as you said, art and science and the imagination. There's been so many great books and still not talked about enough of the scientific imagination. Jacob Bronowski, Tom McLeish, others. I wanted to know about that painting behind you as well.
That painting behind me is my landlord's uncle, and he's going to be very happy
It's always, a lot of us always have a favourite landlord's uncle, and we always like to put up a painting of them. So that's what I would love to know. I would love to find out that actually you then took that painting with you wherever you went. He was my favourite landlord's uncle. I've had a lot of landlords, I've known a lot of uncles, but this one was the one. Achintya, can I ask you, what's your, have you got a show and tell for us? Yeah,
in fact, so one of the things I was considering bringing in was a scintillator plate with these wavelength shifting fibers. So it's interesting that you mention it. I have one of those at work, but it's a bit bulky to transport around, and I don't want to put it in my backpack. So what I have instead is a magnetic tape, which if I can focus in on, you should be able to see this. So this is a real authentic magnetic tape that we store data on at CERN. See the back of it, it's got a number and things like that. So this tape is quite interesting because, and I should now make sure that you can see me clearly. There you go. This tape is quite interesting because what we do, in fact, we have optical technology now, right? CDs and things like that. But turns out that tape is both long-lived and very efficient for data storage. So when these particles collide in the LHC detectors and then they generate data, then we just write them onto tape for long-term storage. And after a few years, these tapes are no longer as good as they were originally. So you make backups and then you get rid of the old ones. So this is an authentic tape that once sat in our data center and recorded some LHC data. So there's about 1 terabyte of LHC data on this, which apparently has 600,000 proton-proton collisions recorded in 2012, I would say. So about 30 minutes of data is about 1 terabyte. And this is amazing. I mean, we have these tapes after we throw away most of the data, right? So we have a lot of particle collisions in these machines. And if you were to store every one of them, you would just run out of space in the planet if you tried to, because you'd have about 5,000 petabytes of data a day, which is a bit too much. So yeah, this is my little show and tell.
See, I love things like that. Sorry, Linda, yes.
Oh, sorry. I just wanted to say that there's one follow-up room. There's this tiny robots, and I like to call it the wee robots room. And if you are on your laptop, even at home, and for any reason you need the data that is on one of those tapes, then you can just say, show me that data, and then one of the wee robots will know exactly what tape to look into, and then physically take it out and copy the data to somewhere where you can actually see it. But if you ask too much, then you're in a queue and you need to wait for all the wee robots to actually go and get all the tape before it's your turn.
That is beautiful. I mean, all those tapes, there's something to me so fascinating in the incredible change in the speed of our kind of accruing of information that in every house now, for anyone certainly of my age, and I would say even all of you as well, which is we have all of these different forms that we've stored information, which are now, they will never be read again. Somewhere within them are facts and thoughts we might have had and measurements, and I find that kind of all of that those lost, almost those lost neurons and their connections in all of those different things is there's a certain kind of beauty to that.
But where's Rosetta Stone? Where's the Rosetta Stone of the modern data world? Because people tend to make copies in one format only. We don't have the equivalent of the three equivalent, the same data saved on magnetic tape, on disk, on a solid state hard drive, and wherever else you might put it. So it's going to be hard to decipher for the future, I think.
Yeah, no, you're right. I mean, already we have so many things that we can't decipher anyway that that you did in 2005. They almost become unreadable, and they said they get turned normally into musical machines by all manner of intriguing engineers.
It's an interesting problem, in fact. So long-term data preservation is indeed a challenge, because, as you say, Helen, when you're doing this sort of data analysis, you have a specific set of software environments and things that you work in, that you program in, and then you go back a few years later and you can no longer. There was some study that said that most scientists aren't able to analyze their data from a few years back themselves. So if you need to sort of make sure that your research is robust and you can go and revisit it after a couple of decades or more. And I mean, this is unique, right? These data sets are unique. You're not going to get another LHC recreating those collisions. So you make sure that you can preserve both the data and the way in which you can analyze it. So there are efforts to do that. Yeah.
Which we're going to now. Questions are coming in, and also if you want to, you can just either tweet us at Cosmic Shambles site, or just or leave under the chat, which is somewhere on your screen. I think there's also a donate button quite near the chat thing, so why not do both? Anyway, so first of all, this question from Forbes. Linda, I'll throw this one at you. Is a fourth neutrino a realistic possibility? And if you can give us a little bit of background as well on neutrinos as well. Then.
Yeah, of course. That's a really good question. And I'll get to the answer. So neutrinos are these elementary particles, are part of the building blocks of matter. I like to think of these elementary particles like the Lego blocks of everything of the universe. And the nice thing about neutrinos is that they've got like a few interesting behavior. And one of them is that, as far as we know, there's 3 flavors of neutrinos. And you can think of your neutrino flavors like your ice cream flavors. And we know when neutrinos travel, are produced from, in a certain context, we can produce them in a particle accelerator, or, for example, the sun produces quite a lot of neutrinos, or a banana produces a lot of neutrinos, an avocado actually produces quite a lot more neutrinos. And
looks like we've got an experiment for you next week then, Helen.
I'll go and find an avocado.
And when neutrinos are produced in a flavor, then they propagate, and they can change flavor when we propagate. And as far as we know, we've measured the 3 distinguished 3 different types of neutrino, 3 different flavors, the electron neutrino, the muon neutrino, and the tau neutrino, which are called like that because of the charged particle they are associated with a production or a detection. So the electron we've probably heard of, which is the particle that sort of like flies around your nucleus in the atom, but the muon is something like an electron, only heavier, and the tau particle is something like an electron, only even heavier. So as far as we know, 3 generations, 3 flavors. So what about the 4th? What does that mean? So that's a really good question, because we currently have quite a few experiments that are looking for a 4th type of neutrino, something that we call a sterile neutrino. And the poor sterile neutrino is called sterile because it doesn't interact with matter in the way that the other 3 neutrinos do. And that's why it's called sterile. But we've had some hints from some experiments in which they've seen neutrinos change in flavor, but in a way that is inconsistent with what we know. So the easiest way to explain it is just to say there's a 4th neutrino, and this 4th neutrino is what is helping, if you want, these oscillations. But that's only in case there's a 4th neutrino and it's quite light, like the other flavored neutrinos. But there's an even more interesting theory in which we have a heavy sterile neutrino. And that's very interesting because as far as we know in the standard model, neutrinos are massless. So the standard model has been fantastic. It's been absolutely a theory that has explained everything. And so far, like even at the LHC, we've been colliding these particles at this really, really high energy. And so far, everything agrees with the standard model. It's amazing. But neutrino oscillations, so the neutrinos that can change flavor, that's beyond the standard model. So the standard model does not predict that. But to sort of like agree with the standard model again, we have a theory which is called the seesaw mechanism. And you can imagine exactly like a seesaw. So we have these very light neutrinos, like the electron neutrino, muon neutrino, and tau neutrino that I talked about, and then which are the ones we've seen and we can produce and we sort of know very well. But then you can think of a 4th neutrino, which is sterile and is also really, really heavy. And that will sort of balance the very, very light mass that the neutrinos have. So there's currently quite a few experiments that are looking for the light sterile neutrinos, so the light 4th type of neutrino. Whereas for the heavy 4th neutrino, the heavy sterile neutrino, that to actually have proof of that, I think we would need a lot. I don't think we currently have experiments that can look into that. We can look into other mechanisms that could bring that together, but those are just some of the opportunities to have that 4th neutrino.
Oh, thank you very much. I hope that answered your question, Forbes. Next one is Achintya. I'll throw this at you initially. This is always something I think people kind of confounded by. This is from Spiderfish. Is it true that almost the entirety of an atom is made up of empty space? If so, then how do we know what remains that is actually real stuff? Is most of what we experience as solid matter simply magnetic repulsion? So there's a lot going on there.
Right, and this is an interesting question. This is something that's quite fascinating, because when we were in school, we were told that in an atom you have a nucleus and you have an electron orbiting it, and you have several electrons orbiting them in these like very well defined shells, and we call this the planetary model of the atom. And it appears as if like the planets orbiting the sun, you have these electrons in fixed places orbiting a nucleus. And it turns out that that's not the case, because you can't really pin down the specific location of where an electron is. It's sort of like a fuzzy cloud in some sort of orbital that is just there in different shapes depending on the energies. So I don't remember the exact the analogy, but if you the space between the nucleus and the first shell, the first electron shell, is enormous. And so indeed, most of an atom is effectively empty space. But in terms of two objects touching, I asked someone this a while back just to get some clarity myself some months ago. And it's not just electromagnetism. In fact, electromagnetic repulsion may not be the best way to think of it. It turns out that you have something that is known as Pauli's exclusion principle, which says that you cannot have two fermions in the same state in the same place, right? So they need to have different properties in some way, different quantum properties in some way. So if you were to try and smush together two electrons into the same atom, you would need a lot of energy to excite one of those electrons into another orbital, because they can't exist in the same orbital. So you would need a lot of energy going into making that contact. So apparently some of the repulsion that we experience as solid objects, and when you slammed the table earlier, right? One hand just doesn't go through it just because it's empty space, is because of this sort of this exclusion that prevents two electrons from being in the same orbital. And then, of course, you can always say, okay, it's because electrons repel each other, but that's just sort of a cop out, I think. Maybe Linda has has a better answer, better explanation for this, because.
I thought your answer was great. I was going to say because electrons repel each other and then stop it there. Yeah.
But can I ask, because I think I was trying to sum this up in the book that I'm writing now, which is getting delivered in 12 hours time, and which I really will be at least delivering enough words to distract the publisher while I edit the book. There's a book in there. I just don't know which words it's in. But it's that idea of that solid things are not solid seems to me to be kind of right, because you see this in popular science books quite often. Oh, an atom is actually mainly empty space, but it's kind of not really, because it turns out that solids are still solid. It's just that what makes something solid is different to what we might imagine. So if you see what I mean, like that idea that if you took all of the thing, took away all the empty space, you would get something that fits into a sugar cube or whatever. Well, that's kind of not how the universe is made. Do you see what I mean? So I think sometimes it's wow, and then you get all worried that matter will forget how to, do it for a while, and the bridge beneath you will disappear. But that's just not how our universe is.
Something even more interesting, which is something known as a vacuum expectation value, and if you want, I guess Linda can tell you a bit more about it, which is essentially if you take like a perfectly empty vacuum, like some volume of the universe, it's not empty, right? It's not empty because spontaneously there is a sort of like energy level there, and antiparticle pairs are spontaneously being produced and annihilating, and so you have a non-zero vacuum expectation value for certain fields, and that is producing particles. So even if you look at like a vacuum, it isn't just emptiness in the sense of us thinking of emptiness. So particle physics is a weird, bizarre world to inhabit.
But I think it says more about humans being bizarre. Robin says we are so deeply offended by the idea that the way we perceive the world is not the way it is. And one of the things that I find interesting about all of this is that people keep going back to those things. And I think most scientists, you go through these things, you're kind of trained to just go, oh, well, they're different sorts of things. There's your experience of the world, which relies on phenomena, and there's the actual. There are scientific descriptions of what's happening, which are models. They're tools to get you to the right answer. They're not saying anything fundamental about the universe in quite a lot of cases. It's just a model that works. And people are so cross that it's not right. And it's really that's the more interesting thing to me, that our brains are so, I mean, we know, because our brains make assumptions all the time, that if you question those assumptions, then everything could go out of the window. Like when two people see a color and they disagree on what color it is. But so I think it says much more interesting things about humans that we cannot accept at all. We will not allow it not to be the way we see it, because we must fight.
Do you think so? It's an ego thing, is it? Do you think it is that bit we're going, well, that table's really shown me up? I mean, I've seen that table, I've had that table 20 years and I've always seen it as solid. Turns out bloody table's mainly empty space. Probably going to burn it now. You know, that there's I mean, it's interesting, Linda, that thing, you know, one of the great philosophical questions and scientific questions, you know, why is there something rather than nothing? But as has been commented about, who says nothing is easier than something?
Exactly. To connect to the fact that in particle physics, we think of, so we know that everything behaves both as matter, but also as a wave. And I think this is something that, again, it's probably said quite a lot, and I'm not sure how many people actually think about it, but I often think about it. Like everything has a wavelength, everything has a wave-like behavior. But for solid things, for big things like, okay, sorry for using the word solid. For big things like us, our wavelength is very, very small compared to like compared to the size of the world we live in. Whereas for particles, like tiny particles, like I was talking earlier about neutrinos, but it's the same for like quarks and other leptons, that wave and matter sort of dual behavior is extremely important. And when I often talk about neutrinos changing flavor, people think of producing one neutrino and then one neutrino becomes something different, which is really not what the process is, because we cannot really say what happens to one neutrino, which is one of the beauty of like quantum mechanics, which is like you don't really know what happens to you can't really talk about one particle. So for neutrinos, we can talk about their behavior when you produce a bunch of them. You produce a lot of neutrinos, and then they all behave like waves, and we produce them, and they're like particles. But then when they propagate, they interfere with each other as if they were a series of waves. And then you have some constructive interference and some patterns of destructive interference. And that's how they sort of change flavor. But then on the other side, so one of the experiments I work on is called NOVA, and we produce neutrinos at Fermilab, which is just outside Chicago. And we produce all of them in one flavor. And we know what we produced, you know. We can cross-check that we produced all of these neutrinos in this specific flavor. But then once they propagate and they move from Chicago basically to Minnesota, they travel 800 kilometers, and then by the time they get to Minnesota, they changed. And those changes are really just patterns of interference, so destructive and constructive interference between the different neutrino states, which then, by the other side, when you see them again, you see them as particles, and suddenly they're like a different flavor. I think that's sort of like mind-blowing, or at least 10 years ago when I joined this field, I was just like, my brain was by that sort of concept.
I think, yeah, we need that. We need that almost on a daily basis. I've found, you know, during lockdown, the fact that human enterprise can sometimes seem so depressing, politics, etc. Whereas then actually there is a genuine. I think the author Colin Wilson used to talk about how poetry could eventually get him out of depression. He would start with a very depressed poem by Edgar Allan Poe, then he would go to T.S. Eliot's Wasteland, and he'd slowly draw himself. And I find the same thing with just listening to scientists, even if I'm not in many ways, I say fully comprehending. Sometimes I'm barely comprehending it at all, but something about that journey of discovery I find it still does that, and that is a good place to be. This brings us to Rowena's question, who this is a question for all of you. I'll start with you, Helen, but she basically said it's not really a question, but can the panel talk about the benefit of blue sky science? I have a friend who constantly says we shouldn't explore space because money could be better spent on X, Y, or Z, and I always fail at trying to explain why it's good to just work stuff out for the sake of it, because who knows what you might find. So Helen, that idea, can you expand on that?
So there's a few things here, but they come into two major categories. And category one is it's good for us. So in one of the books that you showed at the start, Jo Marchant's book, she talks at the end about this terrible thing, awe deprivation. The idea that because we no longer frequently look up at the night sky and just see something that is bigger than us, we are deprived. And not only that, but there is evidence that shows that if someone sees something that is genuinely awesome, just bigger than they are, and like the universe, not the way we see it in cities, but when you properly see the Milky Way out in the middle of nowhere, that you behave more nicely afterwards, you make more ethical decisions, and you see yourself as smaller in respect of everything else. And so I think that there's an important part of curiosity and science, which is just knowing your place in the world and being okay with it being big and exciting and bigger than you. And that's why the moon landings were exciting. It wasn't about the moon, right? No one went to the moon and looked really what the moon was. What they did is they looked back at Earth. They looked at the scale of the achievement. They saw the awe in all these other things. And actually, Apollo was just a route. It was just a way of getting at that awe, which everyone had forgotten for a bit. So that's one thing. So I think there's a lot of, as you say, just those, I was incredibly entertained just now by the fact that the lime sank and the lemon floated, right? Those things make me really happy. And all I had to do was acquire a lemon and a lime to have that happiness. But the other thing, as you pointed out, is that science is continually in the realm of we don't know when it's going to be useful. And even if you're a bean counter, right, that is, like that this person's friend who is watching what goes in and watching what comes out, there is no denying that the biggest advances came from things you weren't meant to be doing or didn't know they were important. Because if you just improve on what you know, it's always incremental. It's a little bit, a little bit more, but a little bit more of the same thing. It's only when you properly take a step sideways and just go, oh, I'm going to have a look at all of that you actually make the really big advances. You need both. But if you cannot do it, it is a complete, the real core of the question here is that it is an absolute misunderstanding and fallacy that you can do applied research without blue sky science. It is not one or the other. You cannot do applied research well unless you have some people, maybe only 10% of them, but you have some people poking around just following things that are interesting just to see what happens. So you absolutely do need both.
Achintya, you must have had to deal with that in, with something like the Large Hadron Collider. There must be, why have they spent all that? Why have they spent all that money just, finding the Higgs field and the Higgs boson? Well, that must come.
Funnily enough, no. Well, not directly, because when the people who do show up on site, when we give them tours and we take them around, they are the ones who have exactly that sort of awe-inspiring experience that Helen mentioned. They come there and it's sort of, it's something so different from our day-to-day life, right? It's on a completely different scale that it does inspire them. They come there with a look of wonder, with this as a place of inspiration. So honestly, it doesn't come up so often. But even when you do think about what have particle physicists done for us, kind of a thing, right? Coming back to Helen's point about Apollo, apparently the mission over its lifetime returned $13 to $14 for every dollar spent on the program itself. And it wasn't as if people were taking all this money and just lighting a big bonfire. It was going to jobs. It was going to developing technology. It was working with industry. There's a lot of this collaboration that happens. So you get a lot back from letting a small subset of people ask these questions and empowering them to do so. And it's the same with the Large Hadron Collider as well, in that a recent study by some economists said that you gain more per euro than you put into it. So it's not a question that we're confronted with all that often. But if you look at how much CERN costs, it's about a cup of coffee per citizen of every member state that is a member of CERN per year, which is nothing. It's also about the size of a mid-sized university somewhere in the US in terms of its annual costs. And when you look at what has come out of it, I'm wearing the T-shirt from the 30th anniversary of the web, right? Which is again an easy sort of get out of jail card whenever this question is asked. Well, we invented the web here, and then you get a lot of economy is being driven by it today. But okay, you could have invented the web elsewhere. There was no fundamental science that motivated the creation of the web directly, but the kind of problems that people were tackling, the sort of data volumes that they were dealing with, the methods that they needed to collaborate with one another, gave you the setting that allowed this to emerge. And fundamental sciences, especially particle physics, has given a lot to other fields. Medicine, for example, everyone knows positron emission tomography, or going to go for a PET scan, X-rays. This came from fundamental science. And even recently, there was people that in Italy, there was a project set up to treat heart arrhythmias using, I think, positrons or protons. I forget which of the two. But again, this is knowledge that comes from fundamental science. And like the majority of the thousands of particle accelerators in the world are used in medicine, not for fundamental science. So of course, people didn't go into it to say, I really want to solve this medical problem. So can we find out why the neutrinos are changing flavor so we can solve a medical problem? No, you go to, what are neutrinos? Okay, they should be massless. The theories tell us they should be massless. Let's observe. Oh, wait a second. If they are massless, they shouldn't be doing this weird behavior. Then you go answer those questions. So I think science in itself has a lot of cultural value, as Helen mentioned, and also gives us something economically and socially as well. You don't do the science for that reason, and you don't have any guarantees. But no amount of what is the phrase? No amount of applied research into the candle would give you the electric bulb. So. But
there's an additional point here, but there's something which I think is really important, which is that one of the things you do have to choose as a culture is sort of you need a bit of blue skies research everywhere, but I think that you can choose where it happens. And I think, for example, that a lot more of these things, fundamental research needs to happen around our planet, because that is our life support system. And if you spend your whole time, all of it, looking out at the stars or trying to go to other planets or looking in on particles, and you don't just have the awe of our life support system, you miss some of the most amazing things. So I think you have to have blue sky science, and you have to have it in all areas. But also, I do think we need a shift that's slightly away from techno amazingness and slightly more into appreciation of the natural environment. And it's still blue skies research, and it's not that you can't have the others, it's just that there's so much focus on technological solutions that actually we're not looking at the way the planet works and saying we need to fit in with it. Maybe what we need to do is not invent a new type of robot. We just need to look at how the bugs are doing it and take their approach. And so I do think there is a decision to make about where you get your awe from. A bit for everyone, but a bit of direction.
Linda.
I think there's like two things that I really liked from your answers. Your awe part of the answer. I think what that really tells us is that science really needs creativity. And I think, again, we go back to how much I think science is actually similar to art, which is if you don't have creativity, you don't get the light bulb, as we were saying earlier. But the second point, which is something that Achintya mentioned, I think it's also, apart from what it is, technology or anything like that, is it's to have a pursuit of research without corporate interest, and that's something that is extremely important. I think the example of the internet is the one that we always do, but like, do we actually then go on and think, was Microsoft that far from inventing the same protocol? And would we pay now if Bill Gates had got there before us? Would we pay to actually surf the internet, not only the connection that we do right now? So there's a lot to have to say to have like these sort of pushes coming from non-corporate places. So, without having anyone looking at their wallet and being like, "Ooh, I can get a lot of money out of this." So,
brilliant. We'll move on because we've only got 10 minutes left. There's lots, but I think there's a lot there, and also the big history. I think that plays. I find that fascinating. The thing, some people might have read David Christian's book about big history, where you stop having that divide between here's civilization and here's science, and actually you go, well, all of these things, they're a connected story. They're not. We could talk often about the fact that divide between disciplines, I think, then creates so many of these kind of either or that don't have to be either ors at all. Let's move on now to the color changes of quarks or quarks. Now, I never know if it's quarks or quarks. I think as it's named after Finnegan's Wake, I presume it was a quark for Mr. Mark, not a quark for Mr. Mork, but I'll leave that up to you, Linda. This is your area. This is Phoebe, who is, she's been watching, initially she says, blame Brian Cox. I always do. And she's been journeying into particle physics. And the bit she's just got stuck on now is she's got down to understanding the color change in quarks. And what she wants to know is what actually causes the color change in quark. She said, is it the gluon itself? And so can you give us a little bit of background as well about what is this color change? And
right. So first of all, quark or quark, I think I actually say them interchangeably. I sometimes say quark, I sometimes say quark. I don't know, it just comes out the way it does. So, right, let's take a step back. What are quarks? We can think of them again as like the building blocks, the Lego blocks of matter and the universe. And so if we go back to our model of the atom, we have the proton and the neutron inside the nucleus. And then we can sort of like think of the proton and the neutron as made up of these quarks. And and gluons are the force carrier of this strong force. And by strong force, I mean is the force that binds everything together. So they're called gluons after glue, because we literally glue like these quarks together, and they are what glues the protons, binds the protons and the neutrons together in the nucleus, and so quarks actually come in different colors themselves, and they can change color, but the color change happens when a gluon is exchanged. And here, I think Achintya can correct me or maybe explain it better than I do. But I like to think of a gluon as a sort of like quark-antiquark pair. So you can think of like a color-anticolor pair if you want to. You can think of on a quark in a specific color, and then with exchanging a gluon, the quark becomes a different color. I don't know if Achintya want to follow.
Would you like to add anything?
Yeah, it's no. I mean, it's something that I haven't fully wrapped my head around as well, because so colors are a way of thinking about the fact that, again, you can't have different fermions in the same space with the same properties. So you needed to sort of invent, theoretically, another property that distinguishes them. And then that's how you get the entire notion of color to start with. And it was really funny. I wanted to bring this up earlier when Helen mentioned about how we just refuse to like accept that the world is a certain way, right? And I think a lot of us in the scientific world tend to do this as well, where we assign terms, names to things that we are familiar with. Particles don't have flavors. You can't taste them. They don't have colors. It's just a term. But no, I think yeah, there is an exchange of particles. So these force carriers, as we call them, these bosons, they exchange, they mediate of a particular force between particles that not agree to that can interact with those forces. So yeah, I think that sort of like changing of color by exchanging gluons makes perfect sense.
We're going to go straight into another one from Matthew Roberts, because he's asked this online now as well and sent it in earlier. The LHC can accelerate particles to 99.9999991%, the speed of light. Could you accelerate it faster at the LHC with upgrades, or would it require an entirely new and bigger tunnel?
I don't remember how many nines there are, so I'm going to believe the number that you gave me.
I'll tell you what. Can it do things faster? Let's forget the 99.9.
This is a very fascinating question. So you see, accelerating particles to higher velocities, higher energies, is a problem not just of accelerating the particles, but of constraining them to a ring. So you build circular accelerators so that the particles can keep going round and round and round, and you keep kicking them as they come by, so they go faster and faster. Now, in order to keep them constrained to that ring, you need powerful magnets. You need magnets that can bend the particles as they go round the bend. So they go straight and then they're bent down, and then they go straight and they're bent down. And you need more powerful magnets in order to get the particles to go to higher energies, to higher velocities as they're going around the ring. At the moment, when the LHC was switched on, it was realized that you couldn't go up to the nominal design energy of 14 tera electron volts in total. So 7 and 7 of two beams that smash into one another. So they started off conservatively with 3.5 and 3.5, then they ramped it up to 4, and now we are at 6.5 and 6.5. We're still off the 7 and 7, right? And the reason for this is that the magnets that we have are superconducting magnets. You need to pump few tens of thousands, I think 14,000 amperes of current through these magnets to get them to generate a magnetic field. Now, your household appliances, your dishwashers, or whatever are like an amp or so, right? So this is 14,000 amps of current going through it. So you can't use copper or gold fibers. They will melt. You need superconductivity. And with these superconducting magnets, they undergo a training process. You need to ramp their magnetic fields up slowly, gradually, at a point where all the fibers in there, the mechanical properties of the magnet say, okay, this is good. I will stay at this field. However, as you go up there can be a sort of very slight buildup of is it resistance buildup? There can be a slight like heat generation, which causes the magnet to quench. So it loses its superconductivity. It becomes a resistive magnet. You can't pump 14,000 amperes through a resistive magnet. You need to get rid of that. So you get rid of it. And then the magnet is quenched. But now it has been trained. So that same intersection or the same point in the filaments will no longer undergo that quench. So you then try ramping it up again. Another part of your magnet may quench. So this is called a training process to get the magnets up to the design, the nominal magnetic field. Now, getting them up to a magnetic field suitable for 6.5 tera electron volts per beam required about, I think it was about 100 quenches or so, right? So you train the magnets and then they quench. There's an average of they will quench, and at some point they stop quenching, so that is stable for that energy. To go from 6.5 to 7 requires about 1,000 quenches. So that's 10 times more. So you lose a lot of time in training the magnets that you could devote to doing physics. So the decision was, hey, we run them at slightly lower energies, and that's fine. So now if the magnets are trained to the point where they can accelerate beams, we can go from 6.5 to 7 tera electron volts per beam so that they can collide. So yes, we can increase them so they will go that tiny fraction of a second light speed faster. But in order to go much higher than that, we would indeed need to build a bigger machine with the technology that we have at the moment, with the cavities that we use to accelerate the particles and things like that. We will need to build a bigger accelerator in order for it to go at higher and higher energies, because for various reasons, you can't kick them as fast. So that's a very good question. At the moment, we can get a 0.5 tera electron volt increase if our magnets are trained, and this is the hope. By the end of the LHC's lifespan, we will get to that. But higher than that, not with what we have.
Well, but higher than that, some of the particles that come from the universe quite naturally. So
yes, much higher. Go on.
Yeah, cosmic rays that I was talking about earlier, which are this natural radiation that comes uniformly, have much higher energy than that. Of course, we can't control it, so you can't collide two cosmic rays to each other. So they're a lot more difficult to study because of that. But those cosmic rays was that much higher energies, like 10 to the 20 or 10 to the 21 electron volts. Those are like approaching the speed of light so much more.
Right. That's thank you so much for that. We've kind of run out of time. I'm going to see how many of these we can get just in case. Ellen would like to know, Helen, can we detect salt levels in the ocean?
Yes, you can do it at the surface. So you can use a satellite to look at properties right at the ocean surface, but you cannot look at depth. So we do have maps of surface salinity from satellites, but it only applies to the top few millimeters. So we can't tell what's happening underneath.
Brilliant. Linda, do neutrinos break the standard model? Is something Christian would like?
Yes, they do, which is what we were mentioning earlier. Neutrino oscillations, they change in flavor and not in the standard model. So we break it.
And while we're still on neutrinos, what is so special about Antarctica that so many neutrino experiments are conducted there? Asked Damien.
Two things. One, they're not a lot of humans, and humans generate a lot of background, especially for these sort of experiments. And two, you have a volume of a huge volume, 100 100 million cubic kilometers of the same material, ice, which is extremely good if you want to detect particles. So it's good for optical detections, like the ice cube experiment does, that has this like sort of inverted light bulbs in the ice, or for radio detection, which is what the Anita experiment does, which flies above Antarctica and just looks down at the ice and looks for radio signals.
Brilliant. Thank you so much, everyone. I'm sorry there's a Carol, Carl, Alan, Melvin, many others. I'm sorry we didn't get to all your questions. There is a kind of a maximum, I think, of 4 questions when you're dealing with particle physics, because there are no short answers if they're satisfying answers. And that was actually great. Thank you, all of you, for joining us this afternoon. As I said, we're going to be back next Sunday, where we have, I think we have 2 of the Trailblazers. If you don't know the website Trailblazers, you should go there. It is a really interesting site, and we're going to be talking predominantly about archaeology, but we can, as I said, we can broaden it out to many of the digging-based sciences. And no questions about bubbles this week, which is entirely my fault, Helen. I apologise for that. If you can support us via Patreon, we really do need that support now, because we have nothing else kind of going on in terms of live shows or anything like that. We're still trying to make 4 or 5 shows a week. If you're able to go to the Cosmic Shambles site, there's various different ways you can support us via Patreon. If you just want to give a one-off donation, that's fantastic as well. It keeps us going in these liveless days. I've just started crossing out dates in my January diary now. January part of my diary. Ain't that fun? Enjoy all of the other stuff that we've got coming up. As I said, Natalie Haynes, we've done a book Shambles with her, which is up at the moment, about Pandora's Jar. It's always wonderful to talk to her. And we also have Paul Nurse. Go back, the first one of the Science Shambles of the autumn that we did was Nobel Prize winner Paul Nurse, talking about what is life. And it's a fantastic book, and it was a really enjoyable conversation on both yeast and skepticism and many other things as well. Thanks very much, everyone, and we'll see you next Sunday.